Okay, so now we are on to problem number 2. Still continuing with 7.5. So those of you that like to write down everything that I say or have on the slides, you probably are going to want to have your own paper for problem 2 and problem 3. They are not going to fit on the note there, I don't think, unless you write really, really tiny. So that's up to you. You can certainly do that. But these ones have a little bit more variety of how much work you want to show. So this time we are given a reaction and then we are given the KEQ. So it says equilibrium constant, which is the KEQ, and we are told that it is 50. So this time we are told something, or given the KEQ value. So then what's going to happen is we're not going to be given something at equilibrium. So find the equilibrium concentrations of all species when the 1 mole of H2 is mixed with 1 mole of I2 in a 0.5 liter container and allowed to react. So it doesn't tell us anything about what the concentration is at equilibrium. We are only told what the initial amounts are. And then again, we're going to change it back into moles when we're done. Okay, so we're going to, again, just to sort of review grade 11 concepts. So similar to the last question, we're going to change these mole amounts into concentration first. And when problem number 2 is different from problem number 3, because when you build the ICE table, you're going to see that these mole amounts are the same. And what that's going to do, it's going to make our algebra a little bit easier. Okay, we don't have to use the quadratic formula. Okay, so like I said, if you think you can write small enough, then try to squish it in there. But if not, I would just get a separate piece of paper. All right, so similar to yesterday, always change to concentration first. That'll at least get you part marks. So we have 1 mole and half a liter. 1 divided by 0.5 is 2. Okay, so again, I'm going to write out everything that I just said. So if you are the kind of person who likes to do that, then write it all out, pause the video, take your time. If not, and you just want to write down the math part, it's really up to you. Okay, so in this question, we are not given any information about equilibrium concentrations, unlike problem number 1, but this time we are given the KEQ value. So what that means is when we go to solve for X, it's not going to be as easy as writing a pretty simple algebra expression using the ICE table and the idea of I plus C equals E. We're going to have to do a little bit more work to solve for X. So we're going to use the equilibrium law. And again, one of the big things about this unit is making sure you write out the equilibrium law with the correct exponents, products over reactants specific for that reaction. And then we're going to use the KEQ value. So it does say here the quadratic formula. That's technically problem number 3. So problem number 2, when you have the same concentration, initial concentration of the two, if you have 2 reactants, then we're going to get a squared in the top and a squared in the bottom, which means that we don't have to use the quadratic formula. If you like the quadratic formula, after we do problem number 3, you can certainly do problem number 2 questions using the quadratic formula. It actually doesn't matter. Okay? It's just a little bit more algebra. Okay, so the equilibrium law contains only equilibrium concentrations. So the information that we're given, this 2 molar up here, this is initial. And so it goes in the I line. Okay, so again, we're going to build our ICE table. Double check that all of the substances are gases or aqueous, which they are here, gas, gas, gas. That's great. We have 2 molar of H2, 2 molar I2, and then it doesn't say anything about the product, which is, like I said in problem number 1, normally the product concentration will be 0. This makes sense. You put in reactants and you make products. So then that means, again, you can't go down from 0. So the product side has to increase. So the change, the X value that we don't know, so again, we're going to use X, is going to be negative for the 2 reactants. And it's only 1X because their coefficient is 1. But then on the product side, so we need it to increase from 0. It can't go down from 0, right? So it's going to be plus 2X. So then when you write the equilibrium line, again, you're doing I plus C. So if this bothers you and you want to write it like this, you get the same. It doesn't matter. That changes mathematically into, when you add a negative, it changes into subtract. Okay? So the same thing would be, the same thing for I2. And then H2 would just be 2X. So in problem number 1, we were able to say one of the reactants, it was equal to a certain amount. We were given a concentration at equilibrium, and this time we are not. But we are given that KEQ is 50. So we're going to use that information. Okay, and we're going to use the equilibrium law. So again, you get marks for this. So please write it out. And so the coefficient of 2 here makes it 2x and also makes it squared. Okay, so that 2 is important. Please make sure you're paying attention to the coefficients. Okay, so when we have expressions like this where you're going to have to solve for x, because functions is not a prerequisite for this class, then there will not be, if you have to do something like this where you have to solve for x without being given an equilibrium concentration, then you have to, it can't be higher than a squared term. So it'll either be x or x squared. Now, sometimes people are like, well, that doesn't make any sense. There are complicated reactions for sure, like combustion, let's say, could have very large coefficients, but usually those reactions are not considered to be equilibrium. Also, we talked about the logic of the number of reactants in a reaction, so you can't have an unlimited number of reactants either. So that sort of limits how complicated these reactions will be. And then if you choose to continue in pure sciences, then reactions can be a little bit trickier when you have more math skills to deal with, trying to deal with those exponents. Okay, but for now, it'll be either x or x squared. So KEQ is 50. Oh, so then products of reactants, so the 2x in brackets squared, and then in the bottom we have 2 minus x and 2 minus x equals 50. So now we have a squared term in the top, and because these are both the same, you could rewrite that like this. That's fine. You have a squared term in the bottom as well. So then you can square root both sides and square root both sides. Sorry. You can square root both sides and in order to simplify things, but be careful. There are 2 answers that says at the bottom for a square root. So we need to consider both. So whether you do the quadratic formula or you square root both sides, we're going to consider both answers. Don't forget to square root the 50. That is a common mistake. You'll square root, it's in order to get rid of the squared term in the x values, lots of people will square root that side, but don't forget to square root this side. So when you square root a squared, then the squared cancels out. And so then your expression is a little bit easier to solve. So the square root of 50 is positive and negative 7.1. Okay, so we're going to consider both of those if you want to divide your paper a little bit. And we have 2x and 2 minus x. So even if we do square root both sides, then you still have a little bit of algebra left to do. So I'm going to multiply to get rid of this on this side, which means you're going to do 7.1 times 2 minus x. You have to distribute, so decide how much work you need to show. So 7.1 times 2 is 14.2 minus 7.1x equals 2x. You need to collect like terms, so bring the 2x over, making it negative, and then dividing by negative 9.1. So the same thing over here, we're going to multiply by 2 minus x on both sides in order to cancel out the 2 minus x from the bottom, the inverse operation, whatever. Then you still have to distribute, collect like terms, and divide. Okay, so when you do equations like this in math, we often do motion. Like in grade 10 math, you throw an object, it hits, what time does it hit the ground? If you took physics, you would have done many of these parabolic motion questions. And what happens usually is one of the answers is automatically inadmissible because it's negative. So time can't be negative. Obviously, you can't go backwards in time. So then it's easy sort of to pick out which root or which solution we don't need. However, in this case, neither of these are negative. Both of them are positive, which is going to be a very common thing. So then what you have to do is use your brain a little bit, okay? So we're never, just like on problem 1, you're never done once you solve for x. You have to take that x value and go back to your equilibrium ice table. Okay, so again, here it all is. If you want to pause the video once it's done and write it all down, when you get two answers, whether you're using the quadratic formula or square rooting, one of the answers will be unusable, or a fancy term, inadmissible. So again, there might not be a negative. Okay, so we're never done once we solve for x. So we're going to go back to the equilibrium line in our ice table and plug the values in here. Okay, so what happens is if you plug in 2.78, which was one of our roots, one of our x values, then what will happen is it will make the concentration here negative. So 2 minus 2.78 is negative 0.78, which doesn't make sense. You can't have negative concentration. Once you got to 0, the reaction would just stop. Okay, so what we usually do, go back to the other side to your work here, and then whichever one is going to give you a negative in the equilibrium line, then you can cross it out and write admissible. So it's inadmissible because it's larger than the initial concentration. That's what's cut off there. Okay, or it gives a negative value in the E line of the ice table, and that is not what we want. Okay, so technically we have not even answered this question yet. Okay, so you have to again make sure that you take the correct x value and go back and answer part A. So what is the concentration in moles per liter of each species at equilibrium? I retyped this question on this slide because it was a long time ago, but on your piece of paper you don't have to rewrite the question if you don't want to. So H2 and I2 are the same. They're 2 minus x. So 2 minus 1.56 is going to give us 0.44, making sure you include units in the concentration value. HI is 2 times x, so 2 times 1.56, giving it 3.12. And then again, part B says change it into moles, and this is just to revisit grade 11 and practice those concepts, and you get 0.22 moles. So often you don't need to do that in the question. You just have to read the question carefully and see what it's asking for. Okay. So problem 3 is very similar to what we have done, except this time now it says how many moles of H2 and I2 are present at equilibrium when 2 moles of H2 is mixed with 1 mole of I2. So now here, these are not the same. Okay, so that is not going to give us a perfect square in the top and the bottom, which means that we have to use the quadratic formula. So again, decide for yourself how much, if you think that you can put this in. There's a lot less explanation in this one because it's very similar to problem 2. Maybe you could fit it in, but if that stresses you out, then either just watch the video and wait and see, or just write it on separate paper. Okay, so same reaction as above. Okay, and same thing. So want to get some part marks? Let's change these moles into concentration. Okay, and now we have concentration and we can build our ice table. So these are initial concentrations. Just as an aside, I don't like capital I's. That's why I always write lowercase i's, but it really doesn't matter. And similar, it doesn't say anything about the initial amount of HI, so we're going to put 0. So again, the reaction is going to go towards the products, which makes sense. So that will increase and the 2 reactants will decrease. Their coefficient is 1 and the coefficient of the product is 2. Okay, so now again, we're doing I plus C equals E. So 4 minus X, 2 minus X, and 2X. We have to do the same procedure. We're given KQ equals 50. Okay, so we do not have a square root in the top or in the bottom. And we have a bit of a problem here as well, because when you use the quadratic formula, you can't, it has to be a certain, oh, that's not a very good color. It has to be a certain format for it to work. That's a V, sorry. Okay, so in order to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a, in order for you to use the quadratic formula, your equation has to look like ax squared plus bx plus c equals 0. And clearly right now, this expression does not look like that. Okay, so we have a considerable amount of algebra to do in order to make our expression into what this is called standard form, into standard form, in order for us to be able to use the quadratic formula. Okay, so I'm going to show, again, there are shortcuts you can take here. I'm going to show all of my work. So we have to FOIL, and then we have to get rid of the bottom of the fraction, like we have to multiply it up to cancel it out. Then we have to distribute, then we have to collect like terms. So there is a considerable amount of algebra to do, okay? So I'm running out of room here. I'm going to rewrite this on the other side, but you might not need to. Okay, so we have to FOIL first. And I'm going to simplify the top as well. So 4x squared. So first, 4 times 2 is 8. 4 times negative x is negative 4x. Negative x times 2 is negative 2x. And negative x times negative x is positive x squared. Okay, there's the FOIL. Now I'm going to, you can even think of it like cross multiplying or multiply this up. Oh, and I'm going to collect the like terms in the middle here as I do that. So negative 4 plus negative 2 is negative 6x. Now distribute the 50. Now we have to collect like terms, bring the 4x over. Okay, so now we have a standard form expression. So the number in front of the x squared is the a, this is the b, including the negative, and then we have c here as well. And so you can decide how much work you need to show for the quadratic formula. If you have a calculator that does the quadratic formula for you, that's totally fine. You can use that. That is not an expectation of this course. Okay, so negative b, so that's going to make a positive 300. Plus or minus negative 300 squared minus 4. A value is 46 times c. And be careful because you can't get a negative under the square root sign. So this, again, you've got the plus minus. You're going to get two answers. So positive 300 plus or minus the square root 16,400 over 92. Oops. So then we're going to get two numbers. So we're going to have 300 plus and minus. Okay, so again, two answers that are neither of those is negative. Go back and look at your E-line in your ICE table, and the 4.65 is too big. It's going to give us negative numbers. And the reactants where we have to subtract. So this one is inadmissible. It's too big. Okay, so again, take your x values, so x equals 1.87, and make sure that you answer the question. So at equilibrium, we have H2 is 4 minus x. I2 is 2 minus x. And HI is 2 times 1.87. Okay, and then it does say change to moles. But this is not going to always be a requirement of this question. These type of questions, so just make sure you read it carefully. Sometimes if it just asks for concentration, you can just leave it as concentration. Okay, so again, make sure you practice as many of these questions as you can. And then the problem number 4 is actually very different. We don't need ice tables at all. So problem 1, where you are given something at equilibrium, you do need an ice table. Problem 2 and 3, you also need ice tables. But again, if you want to do problem 2 questions, there are separate questions listed for homework from the textbook with solutions that where it's a squared on the top and the squared on the bottom. You can certainly do the square root thing. If you prefer to just do the quadratic formula all the time, that's totally fine as well. Just remember that there is a significant amount of work that you need to do in order to get your equation, your equilibrium law expression into standard form first. Okay, thank you.